But when it was compared to how the universe actually looks, there were significant differences. So, was Einstein wrong after all? We gaze up at the night sky, captivated by the glittering stars and galaxies that decorate the cosmos. Yet, beneath this mesmerizing spectacle lies a perplexing cosmic conundrum: how is matter truly distributed throughout the universe? Despite its apparent simplicity, the answer to this question has become a baffling puzzle for scientists. However, a glimmer of hope has emerged in the form of a groundbreaking computer simulation conducted by an international team of astronomers known as the FLAMINGO project. This pioneering endeavor is believed to be the largest ever cosmological computer simulation, from the Big Bang to the present day, to investigate how the universe evolved. The model was based on Einstein's general theory of relativity, the accepted theory for explaining the structure of the universe. However, the results suggest there may be problems with Einstein's work, which predicts how matter should have spread out over the 13.8 billion years since the Big Bang. The results of the new model, called the Dark Energy Survey, show significant differences from Einstein's predictions. So, was Einstein wrong? Join us as we dig deep into how the new discovery of the universe just debunks shortcomings of all modern theories. Einstein created a new cosmos in his general theory of relativity. Albert Einstein reinvented space and time, portraying a universe so bizarre and grand that it challenged the limits of human imagination. An idea born in a Swiss patent office that evolved into a mature theory in Berlin, it set forth a radical new picture of the cosmos rooted in a new, deeper understanding of gravity. Out was Newton's idea, which had reigned for nearly 2 centuries, of masses that appeared to tug on one another. Instead, Einstein presented space and time as a unified fabric distorted by mass and energy. According to general relativity, objects walk the fabric of spacetime like a weight resting on a trampoline, and the fabric's curvature guides their movements. With this insight, gravity was explained. Einstein presented his general theory of relativity at the end of 1915 in a series of lectures in Berlin. But it wasn't until a solar eclipse in 1919 that everyone took notice. His theory predicted that a massive object, say the Sun, could distort spacetime nearby enough to bend light from its straight-line course. Distant stars would thus appear not exactly where expected. Photographs taken during the eclipse verified that the position shift matched Einstein's prediction. Lights all askew in the heavens, men of science more or less agog, declared a New York Times headline. Even a decade later, a story in Science News, the predecessor of Science News, wrote of riots to understand Einstein's theory. Apparently, extra police had to be called in to control a crowd of 4,500 who broke down iron gates and mauled each other at the American Museum of Natural History in New York City to hear an explanation of general relativity. By 1931, physicist Albert A. Michelson, the first American to win a Nobel Prize in the sciences, called the theory a revolution in scientific thought, unprecedented in the history of science. But for all the powers of divination we credit to Einstein today, he was a reluctant soothsayer. We now know that general relativity offered much more than Einstein was willing or able to see. It was a profoundly different way of looking at the universe, says astrophysicist David Spergel of the Simons Foundation's Flatiron Institute in New York City, and it had some wild implications that Einstein himself didn't want to accept. What's more, Spergel, a member of the honorary board of the Society for Science, publisher of Science News, says, the wildest aspects of general relativity have all turned out to be true. What had been masquerading as a quiet, static, finite place is instead a dynamic, ever-expanding arena filled with its own riot of space-bending beasts. Galaxies congregate in superclusters on scales vastly greater than anything experts had considered before the 20th century. Within those galaxies reside not only stars and planets but also a zoo of exotic objects, illustrating general relativity's propensity for weirdness. Neutron stars, which pack a fat star's worth of mass into the size of a city, and black holes, which pervert spacetime so strongly that no light can escape. And when these behemoths collide, they shake spacetime, blasting out ginormous amounts of energy. Our cosmos is violent, evolving, and filled with science fiction-like possibilities that actually come straight out of general relativity. According to astrophysicist Saul Perlmutter of the University of California, Berkeley, general relativity opened up a huge stage of stuff for us to look at and try out and play with. From the idea that the universe changes dramatically over its lifetime, the idea of a lifetime of a universe at all is a bizarre concept, to the idea that the cosmos is expanding, to the thought that it could collapse and come to an end, and even that there might be other universes. You get to realize that the world could be much more interesting even than we already ever imagined it could possibly be. General relativity has become the foundation for today's understanding of the cosmos. But the current picture is far from complete. Plenty of questions remain about mysterious matter and forces, about the beginnings and the end of the universe, about how the science of the big meshes with quantum mechanics, the science of the very small. And some astronomers believe a promising route to answering some of those unknowns is another of general relativity's initially underappreciated features, the power of bent light to magnify features of the cosmos. Today's scientists continue to poke and prod at general relativity to find clues to what they might be missing. And in a recent effort, astronomers have created the biggest ever model of the evolution of the universe, from the Big Bang to the present day, using one of the world's most powerful supercomputers. The model was based on Einstein's general theory of relativity, the accepted theory for explaining the structure of the universe. The new computer simulation that traces how all elements of the universe, ordinary matter, and dark energy, evolve according to the laws of physics. The breathtaking visuals virtually show galaxies and clusters of galaxies manifesting in the universe, fed by the so-called cosmic web. This web is the largest structure in the universe, built with filaments made up of both normal matter or baryonic matter and dark matter. What's interesting, unlike previous simulations that only considered dark matter, the new work carried out by a project called FLAMINGO, short for Full Hydro Large-Scale Structure Simulations with All-Sky Mapping for the Interpretation of Next-Generation Observation tracks ordinary matter too. As Jup Shai, a professor at Leiden University in the Netherlands and a co-author of the 3 new studies on the FLAMINGO project, said in a statement, although the dark matter dominates gravity, the contribution of ordinary matter can no longer be neglected. The project then has already yielded initial insights into the essential roles of neutrinos and ordinary matter in providing accurate predictions. However, these revelations do not entirely dispel the discrepancies plaguing cosmological observations. The computational simulations introduced the complex interactions of ordinary matter, which comprises only 16% of the universe's total value. They must contend not only with gravity, but also with the influence of gas pressure. The unpredictable effects of galactic winds, instigated by phenomena such as active black holes and supernovae, further complicate the dynamics of ordinary matter. Furthermore, the role of neutrinos, subatomic particles with a minuscule but imprecisely known mass, remains a pivotal aspect yet to be simulated. The ambitious project embarked on a series of computer simulations carefully tracking the formation of structures in dark matter, ordinary matter, and neutrinos. The calibration of galactic winds, a significant factor in these simulations, was accomplished through machine learning. By comparing diverse simulations of relatively small volumes with observed galaxy masses and gas distributions in galaxy clusters, the scientists achieved a more accurate representation of these astrophysical processes. The FLAMINGO project leveraged a supercomputer to execute these simulations across varying cosmic volumes and resolutions. Notably, the most extensive simulation involved an astonishing 300 billion resolution elements, each akin to the mass of a small galaxy, within a cubic volume spanning 10 billion light-years. This achievement is considered the most extensive cosmological computer simulation that includes ordinary matter. Matthew Schaller, also from Leiden University, played a pivotal role in the success of this endeavor. He explained, to make this simulation possible, we developed a new code, Swift, which efficiently distributes the computational work over 30,000 CPUs. In addition to providing unprecedented visual insights into the universe's evolution, the FLAMINGO simulations play a vital role in bridging the gap between theoretical predictions and the extensive data collected by advanced astronomical facilities like the James Webb Space Telescope. The current theory beautifully explains how galaxies evolve, but there's a problem. It predicts that they are more closely clustered together than they actually are. The new computer simulation is much more detailed, and it takes into account the role of supermassive black holes. But that's not right either, it's still far more clumpy. So, if the best computer simulation ever created can't get the right result, the two possibilities will happen: either the measurements from the telescope are wrong, or the cherished theories of physics might be incorrect. According to Professor Carlos Frank at the Institute of Computational Cosmology, Durham University, it could be something as big as questioning the basic tenet of our modern understanding of the universe, which is Einstein's theory of relativity. Notably, the FLAMINGO project's significance also extends to resolving a pressing cosmological dilemma known as the S8 tension. That's the debate over how matter in the cosmos is distributed. When investigating the universe, astronomers sometimes work with what's known as the S8 parameter. This parameter basically characterizes how lumpy or strongly clustered all the matter in our universe is and can be measured precisely with what are known as low redshift observations. Astronomers use redshift to measure how far an object is from Earth, and low redshift studies like weak gravitational lensing surveys can illuminate processes unfolding in the distant and therefore older universe. But S8's value can also be predicted using the standard model of cosmology. Scientists can essentially tune the model to match known properties of the cosmic microwave background, which is the radiation left over from the Big Bang, and calculate the lumpiness of matter from there. So, here's the thing. Those cosmic microwave background experiments find a higher S8 value than the weak gravitational lensing surveys, and cosmologists don't know why. They call this discrepancy the S8 tension. In fact, S8 tension is a brewing crisis in cosmology, slightly different from its famous cousin, Hubble tension, which refers to the inconsistencies scientists face in pinning down the rate of expansion of the universe. The reason it's a big deal that the team's new simulation doesn't offer an answer to S8 tension is, unlike previous simulations that only considered the effects of dark matter on an evolving universe, the latest work takes into account the effects of ordinary matter too. In contrast to dark matter, ordinary matter is governed by gravity as well as pressure from gas. Across the universe, for example, galactic winds driven by supernova explosions and actively accreting supermassive black holes are crucial processes that redistribute ordinary matter by blowing its particles out into intergalactic space. However, even the new work's consideration of ordinary matter, as well as some of the most extreme galactic winds, was not sufficient to explain the weak clumping of matter observed in the present-day universe. As Shea said, "Here I am at a loss." An exciting possibility is that the tension is pointing to shortcomings in the standard model of cosmology or even the standard model of physics. So, where did this S8 tension originate? Well, we don't know, which is what makes this so exciting. Ian McCarthy, a theoretical astrophysicist at Liverpool John Moores University in the UK and the co-author of 3 new studies, said. However, computer simulations like those carried out by FLAMINGO could be bringing us a step closer. They may help reveal the cause of the tension because a grand virtual map of the cosmos might assist with identifying possible errors in our current measurements. For example, astronomers are slowly ruling out more mundane explanations for the issue, such as the fact it could be due to general uncertainty in observations of large-scale structures or related to a problem with the cosmic microwave background itself. In reality, the team speculates, perhaps the effects of normal matter are a lot stronger than in current simulations. That, too, seems unlikely, though, as simulations agree very well with observed properties of galaxies. Galaxy clusters and, according to McCarthy, all of these possibilities are extremely exciting and have important implications for fundamental physics and cosmology. However, the most exciting possibility is that the standard model is incorrect in some way. For example, dark matter could have exotic self-interacting properties not considered in the standard model. The S8 tension may be signaling a breakdown of our theory of gravity on the largest scales. McCarthy said, nonetheless, while the latest simulations track effects of normal matter and subatomic particles known as neutrinos, both of which are found to be important for making accurate predictions of how galaxies evolve across eons, they did not resolve the S8 tension. Here's the ultimate head-scratcher. At low redshifts, the universe is significantly less lumpy than predicted by the standard model. But measurements that probe structures of the universe between the cosmic microwave background and low redshift measurements, as McCarthy said, are fully consistent with standard model predictions. It seems the universe behaved as expected for a significant fraction of cosmic history, but something changed later on in cosmic history. Maybe the key to resolving the S8 tension lies in the answer to what exactly drove that change. After all, perhaps like the universe itself, this perplexing cosmic puzzle continues to evolve, with astronomers and cosmologists relying on cutting-edge simulations to unlock its mysteries and refine our understanding of the cosmos. As a noteworthy information, NASA has just revealed how its next big space telescope will allow astronomers to peer deeper than ever before into the heart of the Milky Way after it launches in May 2027. According to the space agency, the Nancy Grace Roman Telescope, or just Roman, will provide an unparalleled view of the center of our galaxy, facilitating the hunt for objects ranging from stars, planets, and icy bodies to isolated black holes. It will do this by monitoring millions of stars in our cosmic backyard and looking for the telltale flickering that indicates something might be passing between its vantage point and these stellar bodies. NASA added that Roman will also have a significant impact on the study of the universe and how it changes over time, called time-domain astronomy. Thanks to its long-term monitoring of wide swaths of the sky over Earth to help it hunt for distant objects, Roman will conduct a survey known as the Galactic Bulge Time Domain Survey, which will use the telescope's infrared vision to stare through clouds of dust and gas that usually block our view of the central bulge of the Milky Way, where a vast amount of its stars are concentrated. Infrared is useful to do this because it passes through these clouds, unlike visible light, which is absorbed by them. Roman will be an incredible discovery machine, pairing a vast view of space with keen vision. Roman's senior project scientist, Julie McInerney, said in a NASA statement, its time domain surveys will yield a treasure trove of new information about the cosmos. Roman will also make use of a phenomenon called microlensing, predicted by Albert Einstein in his theory of general relativity, which says that objects of tremendous mass warp the fabric of spacetime as light travels past this warp. It is curved, and this can amplify the image of a background light source. Roman will use this to hunt microlensing events happening as a planet moves in front of a star in the background, lensing it and causing a temporary increase in brightness. The telescope will conduct the Galactic Bulge Time Domain Survey by taking an image of this central region every 15 minutes for 2 months. This observing campaign will be repeated 6 times over the 5-year primary mission of Roman, creating combined observations amounting to over a year. As Ohio State University physicist Scott Gowdy, whose research is helping inform the strategy Roman will employ, said, "This will be one of the longest exposures of the sky ever taken, and it will cover territory that is largely uncharted when it comes to planets." Roman could reveal over 1,000 planets orbiting their parent stars at large distances and in planetary systems located further away from Earth than ever before. In fact, NASA is already predicting that the observing power of Roman will help set a new record for the most distant extrasolar planet or exoplanet ever discovered by humanity. Planets in the hitherto unexplored reaches of the Milky Way could be vastly different than the over 5,000 worlds currently featured in the exoplanet catalog. In addition to spotting exoplanets in the habitable zone of their stars, defined as the region neither too hot nor too cold to support liquid water, Roman could also spot free-floating or rogue planets not associated with a parent star using microlensing. Using Roman, astronomers will also be able to determine which types of star systems, such as binary stars that orbit one another, are most likely to host worlds around them. This will build on investigations already begun by NASA's Kepler Space Telescope and Transiting Exoplanet Survey satellite. In addition to exoplanets, Roman will be hunting for more exotic objects, including brown dwarfs, the failed stars that form in the same way as stars but do not gather enough mass to trigger the nuclear fusion of hydrogen to helium, the process that defines a star. This investigation could help scientists determine more accurately where the boundary between brown dwarf and star is drawn. As one might expect for such a powerful space telescope, Roman will also make a significant impact in the hunt for neutron stars, stellar remnants that form when massive stars die and their cores collapse to create the densest material in the known universe. The next-generation space telescope is projected to spot 1,000 neutron stars or more. A similar process involving the most massive stars occurs to birth stellar mass black holes, but these are tougher to spot because they trap light behind a one-way boundary called an event horizon. That means that if they are not surrounded by matter to feast on, which they heat to incredible temperatures to emit electromagnetic radiation, black holes are effectively invisible. Yet these isolated stellar mass black holes still have mass and therefore still warp spacetime, meaning Roman can still use microlensing to hunt them when they pass in front of a background star. Roman will have to investigate non-failed and non-dead stars too, as it will allow astronomers to conduct stellar seismology on around 1 million giant stars through analyzing brightness changes as sound waves travel through their interior. This could teach scientists more about the structure, age, and other characteristics of stars. The Space Telescope will also have uses much closer to home than these distant star systems, watching as icy bodies in the Kuiper Belt at the edge of the Solar System, beyond Neptune, reflect sunlight or block the light from background stars. As such, Roman promises to deliver an incredible wealth of scientific discoveries, vastly broadening our understanding of the Milky Way and painting an evolving picture of the ever-changing cosmos. Besides Roman, we can also have high expectations for a mission from the European Space Agency named Euclid. The telescope, launched into space on July 1, Euclid is designed to show scientists more about the dark universe. One of its main goals is to accurately map galaxy redshift, the stretching of light to redder wavelengths as an object moves away from us, as is the case as the universe expands in all directions. Hubble's law tells us that the distance to a galaxy is related to how fast the expansion of the universe is carrying that galaxy away from us, and the higher the recession velocity, the more distant the galaxy and the higher its redshift. Therefore, measuring the redshift tells astronomers the rate of the universe's expansion and the strength of dark energy as it accelerates that expansion. The mission will look back to galaxies that existed as long as 10 billion years ago, or more than double the solar system's age. Over at least 6 years, Euclid will map about 36% of the sky and perform an extra deep survey across 3 smaller fields of the sky, totaling 40 square degrees. Euclid's detectors will conduct 2 cosmological probes. One will study weak gravitational lensing, the marginal bending of light by concentrations of matter. This is useful for mapping the location of dark matter around galaxies and galaxy clusters by measuring how much the galaxy images are distorted by the lensing. The other probe will study baryonic acoustic oscillations, relics of fluctuations in the cosmic microwave background radiation that today manifest themselves in the spatial distribution of galaxies across very large scales. Galaxies tend to cluster in pairs, separated by a standard distance. This standard distance is linked to sound waves in plasma in the early universe. The sound waves propagated as density waves through the plasma and are linked today to the locations of dark matter halos, or concentrations of dark matter associated with galaxies. The size of this standard distance increases over time as the universe expands, so baryonic acoustic oscillations are therefore a standard ruler to measure the universe's expansion and hence the strength of dark energy at different eras in cosmic history. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. Be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.